Good evening, everyone. So first of all, I welcome everyone for joining in to this webinar in the current difficult situation of COVID-19 and wish that you all remain safe and healthy. So this is the sixth talk of the series, and we are very much delighted and privileged to have with us Professor Paolo Giubellino as our speaker today. On behalf of the Alice Star India collaboration, I convey my sincere thanks and gratitude to Professor Paolo for kindly accepting our request and finding time for this talk from his busy schedule. To us, Professor Paolo doesn't need any introduction at all. He has visited India quite often in past, and I believe and I'm sure that Paolo visited most of the Indian institutes, if not all, participating in ALICE. Nonetheless, as a customary, let me very briefly give a brief introduction of Professor Paolo. Professor Paolo Giubellino is currently the Scientific Managing Director of the GSI Helmholtzzentrum and the Facility for Antiproton and Ion Research at GSI Germany. He is an experimental physicist working on high-energy nuclear collisions. He has participated in several experimental projects at CERN Superproton Synchrotron and at the Large Hadron Collider. We all know that Paolo led ALICE experiment at LSC for 6 years, and this was the time during when we got many opportunities to work with him in close association in various ways. Paolo is author of over 400 scientific publications, and he has received several prestigious recognitions and awards, such as 2 Doctor Honoris Causa from Thailand and Ukraine, the title of Commendator for Scientific Merits from Italian President Enrico Fermi Prize, the highest recognition of the Italian Physical Society. Lise Meitner Prize, highest recognition for nuclear physics from the European Physical Society, and many more. Today, Professor Paolo will talk about FAIR, the universe in the lab. Now, I would request Professor Paolo to enlighten us. So, Paolo, you can take over now.
Okay, so thank you very much. It's a pleasure to be with so many friends. Indeed, are mostly people on which we had many occasions of being together in different instances. And it's a real pity, on the opposite, that this has to be done virtually. But okay, that's the situation in which we all are at the moment. And I really, really wish that everyone is safe now, and that you are really putting always safety first, as we are trying to do in our laboratory. These are difficult times, and I must say they are difficult, especially for the young scientists, because you of you that are young and students and so on are the first victims of this. We often get from the governments and so on congratulations that things are progressing and we are doing a bit business as usual, but it's not true. There's nothing like the human interaction, like the discussion at the coffee with your professor or your more senior colleague of being at the experiment that help developing your own scientific future. And so I really hope that this will not last much longer, and that we will be back at a situation in which you can fully profit of the learning from the environment of science. So, okay, the title of my presentation is FAIR, the universe in the lab, and this is the motto of the laboratory. But I would like to say this is one section, let's say, of our scientific program, and I will concentrate today on that, although our scientific program is way, way broader. it is a very interesting moment for the interplay between the nuclear physics, astrophysics in the sense of observations of messages coming from space, and this in what is now becoming the standard of multi-messenger astronomy, in which you look at different signals coming from a certain source in order to disentangle the various processes which are going on there, from the gravitational waves to the emission in the visible light. But neutrino astronomy is becoming a major factor. And but what we know, and we should always keep in mind, is that the processes which are happening up there, that are at the origin of the signals which are observed, are nuclear processes. From the simple fact that the sun is burning, and is burning through a nuclear fusion process, all the way to the neutron-star mergers. These are nuclear processes that gain understanding from the fact that nuclear physics progresses, the nuclear physics experiments progress. It's clear that one of the beautiful things in this is one of the fundamental questions that was listed, like the 10 fundamental questions of science 10 years ago, is where the elements, especially the heavy elements, come from. And they come from many star generations that produce and distribute in the cosmos the remnants of the nuclear processes which have happened in there and result in what we are, that is star stuff. Now, why FAIR is being built in Darmstadt? Well, because in Darmstadt there is GSI, and GSI is the reference laboratory in Europe for nuclear physics. And it's been like that for at this point more than 50 years. Actually, this slide I must correct. We are now over 50 years. It's 50, almost 51. In a month will be 51, and also our celebrations for the 50th birthday have been victims of the COVID, and it's been a laboratory where major discoveries have taken place. If you just look at the periodic tables of the element, there's 6 which have been discovered here, and that's why there is something which is called the Darmstadtium, from the city of Darmstadt where we are. There's something called Hassium from the state of Hessen, in which we are. And if you look at for example, at the isotopes tables, you see the usual number of neutrons or number of protons. The black ones are the stable ones, the others are the artificial ones. And you see that if you go towards the edges of the plot, I mean, clearly time goes away from the edges. The more recent discoveries are at the borders. You see that almost all of the new ones have been discovered at GSI, all the green, all the red ones. And but there's many discoveries which have been done here, and that I will not mention. I mean, which like, I don't know, the most precise measurement of the mass of the electron has been done here. The most precise measurement of the relativistic time dilation has been done at the ESR storage ring here, which, by the way, in a very simple, conceptually and beautiful experiment, in which you induce a certain transition in a nucleus by shining a laser either in the direction of the motion of your ions or in the opposite direction, opposite to the movement, and you measure then the time dilation with the precision of 10 to minus 8, which is really fantastic. But there's also fundamental discoveries. I mean, practically everyone in this virtual room works on phase transition from the hadrons to the plasma, but we should remember that recently the transition from the liquid to the gas phase in nuclei was discovered here at GSI, and recently, I mean 10 years ago. And this is actually was a beautiful caloric curve that you can see here with the latent heat. So you have the two curves of the heating, first of the nuclei and then of the fragmented nuclei with part where you have to overcome the latent heat. And this is the type of curve that we would always be so happy to finally be able to show with measurements at the organ plasma. If there was a first order transition, this is what one would see. But also there are fundamental application discoveries here. The one we are most proud of is the therapy for cancer with the nuclei that was developed on campus. Actually, 440 patients were treated here in GSI before the technique was transferred to specialized clinics. I don't need to explain to you how that works. You all know very well that if you use a heavy ion to ions, these are not heavy, I mean, it's light ions, ion to deposit energy, most of the energy will be deposited near the end of the range in the Bragg peak, while if you use photons, then actually the maximum is near the entrance of the body. So if you want to spare as much as possible the healthy tissue around your tumor, this is a major breakthrough. And of course, it's particularly relevant when the tissue around the tumor is particularly precious. In the brain, in the eye, in the spinal cord. And this continues to be a major, we'll see later, area of development. But also in the field of computing, and here is really a coupling. As you know, a lot of the energy, a lot of the cost of a computer center is in the energy which is consumed. The energy with which you power your computers and the energy which you spend to cool them down. The first one you cannot really do much about because you have to power your computers. The other one you can try to minimize with smart design, and this is at the moment the most energy efficient large system of computers in the world, and it actually got a specific recognition, which is called the Blau Engel, for being a green technology that allows energy consumptions to be minimized. So what happens now? It happens that GSI, which is one, I hope you are seeing my cursor. Are you seeing my cursor when I move it around the table?
Yes.
Good, thanks. So this one up here is GSI, which is the existing laboratory, and this is FAIR, which is under construction next to it. And FAIR is a huge jump. It's first of all, it's considered a landmark for European science. These are the top research facilities in Europe in each field. For example, for particle physics is the LHC, are so-called S3 facilities in Europe, and this is the one for nuclear physics. It is being indicated as the top priority of the European physics community in its long-range plan, but it goes way beyond Europe. These are the countries which own the laboratory, and you see most notably India here. And in fact, this is a much larger enterprise than GSI has ever been. If you look at the sheer numbers, it's 2 million cubic meters of soil that has been moved, 600,000 cubic meters of concrete, and 65,000 tons of steel that Germany would not do alone. This is done by a consortium of countries that are the one in orange in the picture up here. You've seen the flags before, that are, strictly speaking, the owners of the laboratories. The laboratory is a stock company of which these countries own the stocks. So from a legal point of view, India has a laboratory in Germany. It's on German soil, but it is owned by the countries in orange. And then there are all the countries in blue, which participate in the experiments and are simply like most countries work at CERN, simply members of the experiments and so on. There are, at the moment, more than 3,000 scientists involved. And India has been one of the founding members. This was already in 2007, but I think it goes really beyond this. You know that in aviation physics, India has been among the countries which have been on the forefront from the start of the heavy ion program at CERN, all the way through the years of Rick, through the development of the experiments at the LHC, after the very successful experiments at the SPS at CERN, and then in the development of the aviation experiments at FAIR. This is, so in some sense, India is not a participant. It's been one of the countries where the facility has been conceived and where the idea of FAIR has been developed. And that is also resulting now in a very, very lively community. I'm always impressed when I really look at the simple list of institutions that you can see here. I mean, these are the institutions which participate at FAIR from India. And as you can see on the map, they are from really all over. I think there's only a couple of states where we don't have an institution. We should work on that. And also there are people that have top roles in the facility. In particular, the highest scientific instance of FAIR is the Scientific Council, which gives the directions, the strategic directions of the science, and is chaired since quite some time by Professor Raha from Bose Institute, who I don't know if he's connected now, but this is really the top science position of FAIR at the moment. Plus, very many other colleagues have had key positions, in particular, of course, Vika Singha, who's been sort of the inspirer of this whole operation. Now, how the facility looks like. This is GSI in blue. In red is FAIR. These are the FAIR accelerators. Although some of the accelerators on the GSI soil will be used as injectors to the FAIR accelerators, like the linear accelerator and the first synchrotron CIS-18. But even more, there is a group of low energy storage rings, the ESR, crying, and HITRAP, which belong to FAIR but sit physically on the GSI campus. So FAIR is this in terms of new buildings, although most of the accelerator complex of GSI will also be integrated into FAIR when the time comes. The jump from GSI to FAIR is huge. The key parameter that grows is the one which is already what characterizes GSI as compared to most other laboratories in the field, that is the beam intensity. And intensities will go up by 2 to 4 orders of magnitude. You might wonder why, how can there be a variation in the intensity? Because what one uses, so you have a linear accelerator, then a synchrotron, and a second synchrotron. Then you can either use the beam directly, fixed target, here this is CBM, or you use it on a target, and then with the fragment separator, you select the secondary beams. Now, the intensity of the secondary beams depends on three factors: on the intensity of the primary beam, which goes up by a factor of 100, on its energy, which goes up by an order of magnitude, and on the acceptance and structure of the fragment separator, which is an immense object that will allow to get a further dramatic increase in intensity. So when it comes to the secondary beams that you use down here, the intensity can be up by even a factor of 10,000. And then you can collect either these secondary beams through this line in these storage rings, or you have the same path but with protons, and on this target here you can produce antiprotons that get collected again in the storage rings down here. So that's why antiproton and ion. Antiprotons are produced with a new LINAC that accelerates very intense proton beams, and that then on this target down here are used to produce antiprotons that are then collected in these two rings. Or you accelerate ions, and then you either use them directly or through the selection of the fragments in the fragment separator. Now, what one wants to do here, one has 4 pillars, so-called, of science. And you will come from bottom up. You can use the antiproton beams to study the structure of hadrons and their dynamics. And this will be done by the PANDA experiments. You know that there were very sophisticated experiments which did the hadron structure using antiproton beams at CERN and at the ISR and at Fermilab. And now most of the work is done with electromagnetic probes, but that is a much more restricted access to states. And this will be really the next generation of hadron structure studies of very, very high precision. NuSTAR is not an experiment, it's a family of experiments that address nuclear structure and especially nuclear astrophysics, the reactions that are at the basis of the structure of the universe. And we will see quite a bit of that later. And then we are talking about the exploration of the phase diagram of strong interacting matter. And okay, many of you are working in this region where ALICE operates at very high temperatures and very low net baryon density. Many of you are working in STAR, and STAR has been doing more and more in pushing first by lowering the energy at RIC with the big energy scans, and then even having a fixed target program to go to the higher baryon densities this way. And where we will be working is down here at the lower temperatures but very high net baryon density. Last but not least, the upper pillar contains many actually very different things: atomic physics, biophysics, plasma physics, material research that are been at the time of planning FAIR put together under one name, although they are really very independent collaborations which look at a very broad range of things. So, as I was saying, one of the questions that we are addressing is really where and how were made the heavy elements in the universe. If you look at the universe just after the Big Bang, how we look at it in ALICE, we know very well. We do produce some nuclei, but they are very light nuclei. But how did all the rest of the population of the periodic table come about? Well, through a number of processes all along the history of the universe. And those are the ones that we do reproduce in the laboratory so that they are, it is possible to study them in detail at FAIR. Now, I was telling you about the fragment separator, so this is one of the elements we will see later, but there are many processes like supernovae and star burning that will be studied directly through the reproducing critical processes in the various experiments which sit beyond the fragment separator. If you send your uranium beam on a production target, this picture down here, which you will not see very well, but this is the typical picture that you get with many different possible isotopes produced that you select with this very large acceptance separator, and then either use directly or decelerate to use. Why do you need to decelerate? Well, because most of the reactions which are of astrophysical relevance are actually happening at very low energy. So you need the high energy to produce and select the various isotopes, but then the measurements of the cross sections that you want to do that are of relevance to understand the universe are actually at very low energy, so you have to decelerate them. And also you want to store them in your storage rings and be able then to reuse the precious rare isotopes that you have produced over and over again. Now, to give you some examples of things that one would measure, one that I find fascinating, in 1983, so we're at this point, we're 40 years ago, Fowler, in his Nobel lecture, indicated as one of the most important processes to measure the process of the alpha fusion on carbon-12. Why? Because, well, those are the building blocks of life, carbon and oxygen. And we know carbon and oxygen are produced in late stage of the life of stars. In stars, you have burning of hydrogen to make helium, then you burn helium to make carbon, and then you take the carbon and another helium, and you make oxygen. So this process is actually, we know that it's the process which creates the oxygen that we breathe, but how much oxygen, how much carbon, this relies on a cross-section which is very poorly known, and that we will be on the opposite measure, finally, 40 years later, measured at FAIR. Another one which is fascinating is, you all heard about this fantastic new measurement done by our friends which study gravitational waves, in which they managed to measure the merger of two neutron stars and have the observatories measure the light emission that follows. Now, this is the light emission curve following the neutron star merger. The red points are the measurements, and the blue curve is the theoretical curve that with which they compare the results. And well, this is from a period in which it was still unclear when this would ever be observed. But just to stress it, Martinez, Pinedo, and Darcones are theorists from GSI. Why were they working on something exotic as a neutron star merger? Well, because that is exactly one of the processes that we will reproduce in the laboratory at FAIR. Not only it's one of the most satisfactory ones, because they are addressed by all of our pillars that I was telling you before. Actually, the word kilonova, which is now used everywhere to describe this light emission process following the of extreme intensity following the neutron-star merger was coined in this paper by nuclear physicists. So there you have a very complex puzzle that you have to disentangle, and where you have each one of our 4 pillars bringing a piece. You want to know how matter behaves in extreme electromagnetic fields, and that's done by APA. You want to know the behavior of nuclear matter, of how strongly interacting matter at very high densities and temperatures, and how then the equation of states evolves throughout the merger. And this is done at ADES and CBM. But then you want to understand how protons and neutrons form, and how hyperons interact in the systems, and that's done in PANDA. And last but not least, in a process like this, you will not produce your ordinary nuclei. You produce exotic, neutron-rich isotopes that then decay and evolve to finally populate the periodic table with the proper amounts and abundances that we know, in particular of all the heavy elements. Almost all the platinum and gold we know come from neutron-star mergers. And this you put together then with the measurement of directly all of these processes of the evolution of these nuclei produced in NuSTAR. So what the first question you might want to ask is, are you actually reproducing those conditions in your experiments? And then you look at what are the temperatures and densities that you have in neutron stars, maybe 10 times the nuclear density, and in the mergers of neutron stars, where the temperature goes up. And then you compare collisions in, for example, CBM, and you see that indeed you get the temperatures and densities that are relevant to the understanding of this process. But there are many other processes in the universe. I told you about supernovae and so on, but let's come to other processes. Well, you know very well that we have beautiful pictures taken by all sorts of satellites, but now even samples taken from the surface of planets. But what do we know about the inside of planets? Even of our own Earth, we actually know very little about the structure of of the inside of planets. And planetary science will be a major part of the APA program, in which at FAIR, one will have the very special situation in which one can have, it's the only laboratory in the world, energy deposit done with nuclei and measurements done with petawatt laser, and all possible combinations of the two in a pump probe system. But let's go beyond. Universe means also the space. And again, we are all now excited by the fact that finally Mars and very long trips are again on the map. And well, not all is nice about that. If the life on Mars or along the trip means exposure of people and of equipment to very large radiation dose. And in particular, if you look here, for example, the probability of cancer death in the Mars mission starts to be substantial. I mean, these are several percent of probability. Then you have a crew going. If you have 8% probability of dying of cancer along the way, that's not fun. And moreover, there are issues with cognitive capabilities affected by radiation in the brain and so on. All this is now major activity at GSI, and will be even more at FAIR, which has been identified by the European Space Agency as their ground laboratory for radiation studies. But there's many other aspects of our universe that you can study if you have a laboratory with the ion beams. One, again, which relates to the building blocks of life is the fact that you can irradiate astrophysical ice grains and see if you indeed form amino acids, and you do. And this is, for example, something which is not so unique of our laboratory. There's been many studies. So why both these studies and these are particularly well done here? Because this is the only laboratory in the world where the proper spectrum of cosmic rays in the relevant energy range that is relevant for the formation of these structures and for the damage can be produced and used. So even, for example, recently we've been approached by also other space agencies, including NASA, that would like to measurements here, because this is the only place where you can actually have a realistic description of the spectrum of cosmic rays. And this is done continuously developing new technologies. Let me mention one. Okay, there are the usual things that you always hear: detector instrumentation, material research, accelerator science. One thing that I find particularly cute is nuclear clocks. Well, the highest precision that we have in clocks at the moment are atomic clocks, and they are extremely precise. So why would one want something even more precise? And what promises to be, a nuclear clock promises to be maybe 100 times more precise than an atomic clock. Well, one for all, every one of you every day uses an atomic clock because you use the GPS. And the GPS, as you can see from your own Google Maps, is precise to some meters. Now, meters are not good enough for self-driving vehicles. You want centimeters, so 100 times better. In particular, think of an airplane which is landing and that you want to guide in fully automated way using satellite information. Well, you want that to be known to centimeters, not to be known to meters. You would not want to be on that plane if it was guided with a meters precision. And so development of nuclear clocks require knowledge on certain specific transitions that are possible to measure in our storage rings and will be measured, and that will be the, let's call it, the scientific basis then for the technology development. But a lot is to be done as the successors of the therapy developments that we have done here. In particular, there are two frontiers. One are the moving organs, like the lung. We said that the precision of the energy deposit is what is a big advantage of this technology. Of course, if the target moves, your precision has no interest anymore. So you have to have different approaches. One could be the very high speed in your irradiation, so that the organ doesn't move on the time scale of the irradiation, or a smart system that follows the tumor. There are a number of different ideas, but also there are other points that are being developed now that are, for example, the immunological approach, in which you couple the therapy with the ion beams, with the immune response of your own body. It's a fascinating new field where, for example, one of our collaborators is a name that you certainly have heard a lot in recent times, which is BioNTech. those which have developed the vaccine with Pfizer for COVID. But also you have a system which can destroy cells at a well-defined place in the body. But then in practice, you have a remote scalpel, like in a science fiction movie. And so what has been done has been to experimentally do heart ablation on 12 pigs. This was done 2 years ago, and see how the beam of particles can be used really as a scalpel. And it worked beautifully. So it is indeed the proof of principle that one can actually use the particle beam as a scalpel for surgery in special conditions. This, of course, would never be for ordinary surgery, but in particular conditions, it could really be very important. And so on and so forth. There is now, for example, a number of programs of applied research linked to the pandemic, both on vaccine developments and viral detection, membranes for protective masks, and so on and so forth. Yet, when one talks about applications, when one talks about why what we do is important for society, there's always these 3 pillars. One is the advancement of knowledge, which I think is always should be the sort of the underlying motivation for all we are doing. But then there is the second, that is the technology developments that then are applied in all sorts of different fields. I showed you a couple of examples. But in the end, science is done by people, by brains. And we are very proud of being a talent factory, a place where young people are offered the conditions, not only physically here, but working together with us, conditions for development of their own capabilities that then get applied either in research or in industry or in teaching and their term. It's still, this is know-how, this is knowledge, these are talents that then are pumped into society at large. And this, in my personal opinion, is probably the greatest value that we produce for society. So in particular for this, we have developed a program which is called Get Involved, that brings, that enhances our capability to offer internships to young people of all sorts of levels. And you can see here, they come from a bit all over the world. And there is a wide range of the research experiences that one can have, internships, trainees, and so on. And I must say, quite a few young Indian scientists have profited of this. And please do, if you are interested, look at this website of the Get Involved program, which is, by the way, run by a scientist of Indian origin who's particularly keen to promote the presence of young Indians here, Pradeep Ghosh. So, where do we stand? I will try to briefly update you on where we are on the construction. You can find, by the way, on the internet always little drone videos, but let's say the construction of the buildings progress is really fast. And I would like to show you some examples. In December, the CIS-100 tunnel the trench was completed, and the first slab, the floor, let's say, of the accelerator complex was also completed. This clear white is the oldest piece where we started the construction, that went all around, and then it's joined here. So, and already in February 21, so 2 months later, you see the walls of the tunnel growing. And this is a CBM, which is the one which for many of you is the most interesting one. This you see from the cave of CBM, which now only lacks a roof, which is going to come very, very soon. Actually the beam dump for CBM is now being filled with slabs of, which is at the back here, which is slabs of iron, so that this is done before putting the roof, because it's of course done with huge cranes. And these are the tunnels that, as they look to now, you see that this is already, this part of the 6100 tunnel has already been recovered with soil, and now there are the buildings on top of the surface that are growing. This is the part which is still being constructed. Back here is the building which houses all the interconnections between the different beam lines. This is the beam line from CIS18, from GSI. This is GSI up here. This is the beam line from GSI18. And at the back here, you see the construction site for Darmstadt. And the accelerators keep piling in. All of the dipole magnets and all the RF cavities have been manufactured. A lot of components from the other parts are already on campus. We have rented huge storage places outside of the campus to store all this material. And I must say, some very important components of our accelerators are built, or have been at this point built in India. From the 600, these are huge units of power converters that are used for the magnets. They are being built in India, but so also beam diagnostics, beam catcher, cables. These are the 162 power converters already done in Hyderabad. And here the beam diagnostic vacuum chambers, again from Vacuum Techniques in Bangalore. For the experiments, so we've seen progress in the civil, progress in the accelerators. The experiments, you see the constructions is approaching halfway, and for all 4 pillars. And of course, these are the typical photos of some components, but I would like to rather show you some components which are built in India. These are for the CBM experiments, the GEM detectors that will be used for the muon spectrometer. These are constructed in collaboration by VCC and Bose Institute in 12 Indian universities. Both the electronics and the detectors are made in India. So is the high-resolution gas detector for nuclear structure for the NuSTAR experiment, one of the neutron time-of-flight spectrometers, pending traps. And there's again a large collaboration of different Indian institutions building these. And this is a view of real life. This is happening now. These are modules of the GEM detectors built in India, integrated in the so-called mini CBM. A mini CBM is a slice, essentially, in acceptance of the future CBM experiments, so that all of the detectors can participate and be tested together and studied in terms of timing, in terms of data flow, in terms of real-time data processing. And these are the first results that were obtained in last year, and now there is data taking ongoing. And this is interesting because it was really an example of mini CBM of how you can handle work when the pandemic strikes. There was a continuous screen with people working remotely from different institutions, both to discuss and advise on things, but also to directly operate detectors from the remote locations. So this was a really exercise in turning some of our experiments into space devices, satellites, which you have to painfully operate from far away, but it worked. So what happens to the science of FAIR? I have still a few minutes, and just to tell you what happens to the science. This is by the way, the drawing of the facility FAIR and GSI with little blobs for each one of the 4 pillars in the location where the experiments will be. So you see the APA experiments at the low energy rings that I told you are on the premises of GSI, but also at the other storage rings. And here, this is a CBM, which gets the direct beam from CIS-100. These are the NUSTAR locations on the storage rings and on the downstream of the fragment separator. And this is PANDA, which uses the high energy storage ring with the anti-proton beams. So it still takes a few years before all this is in operation. So how do we get there in a way that not only the experiments will work, but also that the collaborations will have matured in the meantime and grown? Well, we do a so-called precursor science program, which we call FAIR Phase 0. It has started already a couple of years ago, and uses the beams provided on the GSI premises and the components of the FAIR experiments, which are already available. And we have about 3 months of running every year with experiments selected by an international committee. I must say that the response of the scientific community has been overwhelming. We get requests which exceed the amount of beam time that we are able to offer by factors of 3 or 4, depending on the beams. And this was the case when we had the first call 2 years ago, and it repeated itself even more overwhelmingly this year when we had, last year, sorry, 2020, when we had the second call. And you see here the way the whole thing looks. You have, this is the GSI basic facility. Then these are the low energy rings, which are already FAIR rings, although they are on the GSI premises, Cry ring, high trap, and the ESR. The small fragment separator, compared with the huge fragment separator that will be in FAIR. And here are all the experimental halls that are offered. This is really a reason of great pride for us, the fact that although there's only a limited number of months of running, we can actually offer a lot of science because these facilities manage to run in parallel. We can even have alternating bunches of different ions that are accelerated together and then distributed to different users. So that you don't want to read these lines, but what I can tell you is that each one of these lines is an experimental hall. And you see that you can have in this certain periods at the same time up to 6 different experiments running contextually. And this sort of like expanding time, these 3 months are in reality a lot more experimental time for your experiments. And indeed, everything is working right now. In this very moment, we have uranium beams accelerated and then distributed to this whole system, while calcium beams are distributed to this other branch at the same time. And you see here, this is the situation in this moment, uranium and calcium for these different experiments at the storage rings or with fixed target. I will not try to describe any of the experiments, but just to give you a flavor, a few years ago, this watch was exposed to our proton microscope for a proton radiography. That is one of our tools for the study of plasmas. And this was the picture. And this is how it looks now. You see the jump in resolution is the jump of the quality of our technology. These here, these are blobs of identified nuclei for studies of nuclear structure. Many of these are new isotopes which have just been discovered in this month. Down here is again mini CBM. You saw the data taken of last year in the previous slides. Now there's going to be the first physics benchmark of observable lambda hyperons. So we really get into science capabilities, and that means training the full system with up to 2×10⁹ ions per spill. This number is very, very important. Why? Because we all know there's been experiments done in this energy range in the past. So what's the point of doing these new experiments? Well, is that one works in a totally new regime of intensities. There's 3 orders of magnitude in intensity compared to the previous experiments. But then you have to have an experimental apparatus which is capable of handling those. Otherwise, there's no gain. But that is not trivial. And in particular, you have to have a completely new approach to the way you treat your data taking. So it's triggerless, and then you immediately transfer all the information to that green cube, the computer center that you saw before, and you do real-time data analysis. Here you have the precision spectroscopy in dry ring. First time it is used for the experiment. Laser spectroscopy of super heavy elements. These are unbelievable things. You do chemistry or nuclear structure of nuclei, of super heavy nuclei that are produced in numbers of units, 3, 4, 5 in a running period, and live for a very short lifetime. And yet you manage to do spectroscopy, to do chemistry with them. It's really fantastic. Biophysics, I told you before, the adventure continues. This is the first study of irradiation of a tumor with a radioactive carbon beam. Why do you want to do this? You don't want to do this in everyday therapy, but in research on these cancers. It is fantastic that you can do at the same time PET images of the tumor while you are irradiating it. And this is a completely new development. Just first TARI has been done this year here. And so on, material research, fission. I mean, I will not go through all of them. So, because my time is up, it's 4 p.m. here, so I think it's the time in which I have to conclude. I hope I convinced you that FAIR is a unique opportunity for world science. There is a very broad program. I gave you some examples. There are many, many, many more. We want to make this a global success altogether. And for that, we believe that a very crucial aspect is not only the commissioning of the hardware, but is the development of the human capital that will then exploit the full facility. And this is done through this precursor program. It's called FAIR Phase 0, which is ongoing. I reminded you that India has been a founder and a designer of this project. It's a leading player. A lot of the accelerator components, a lot of the detector components are built there. There is a scientific community which has been at the origin of the design of FAIR, of the definition of FAIR, of how FAIR will be. And it's indeed one of the largest common programs for Indian research. You saw how many academic institutions and industries are participating. So we really look forward to a continued special relationship with India as a driver of this program throughout our future. So thank you. This is what I wanted to say.
Thanks, Professor Paolo, for very nicely explaining various aspects of science program of FAIR, its various applications, current status and progress of the fair construction, and of course highlighting the role of India and Indian participation to this endeavor. So I think we have some time to take a few questions. So I request, if you have questions, please raise your hand and then we can take up one by one. Or you can speak, you can unmute and speak directly. Can you hear me?
Maybe I can start, Siddharth.
Okay.
Paolo, this is Vashish. I have one question. Is there any plan of collaboration with, let's say, this large experiments who are looking at gravitational wave and neutron star merger? Because there is a lot of physics overlap, as you have explained also in your talk. Is there any thoughts on this?
Oh, yes. Well, there is a, as I showed in the very first slide, the collaboration goes a little bit through the simulation and the theory, which we both use together. But there is, for example, there was, as a starter, a beautiful Emmy task force meeting a couple of years ago, in which people from the different communities came together. A program has just been approved by the state of Essen, which is called Elements, joining together GSI, the University of Darmstadt, and the one of Frankfurt, with theorists in nuclear physics, theorists in astrophysics, and experimentalists that get together exactly to work on this connection. There was last year, I think, no, 2 years ago at this point, an issue of PRL that had as the three highlighted articles, looking into the nuclear aspects of neutron star mergers. So it is a hot topic now. And I would imagine that this can be actually also pushed in other communities. There is a strong community in India that is interested in gravitational waves. There is a strong astrophysics community. There is a strong ion community. I think that these should really talk to one another, because this is now happening here in Europe, and I think it should be really done also in your environment. It is extremely interesting.
Thank you.
Siddharth, can I ask?
Yes, Pradeep, so please go ahead.
Hi, Paolo. I'm Pradeep Sahu here.
Oh, hello.
So I'd like to ask maybe very simple and silly question that we are exploring in CBM, especially in CBM, that we are exploring the energy level up to maybe 30 or 40 GeV per nucleon center of mass energy. So now recently, see STAR experiment and even SPS are trying to do the same type of energy. So of course that we can say that this is more luminosity, more and more intensity of beam. But I would like to say that will it keep the same physics, or it is that we are exploring something new in CBM?
Well, as you know, by going up in intensity, you do explore different physics, because you have access to variables that otherwise you would not be able to observe. So you have a combination. On one side, you have an apparatus which is designed for this geometry. So it is actually, it's a forward spectrometer. STAR was designed for collider operations, so it's not optimal for forward, but that is a minor aspect. The big aspect is that you have several orders of magnitude of intensity. Of course, is important only if you go up by orders of magnitude. If you are made a factor of 4, then you say, okay, just run star longer, and then I get the same stuff. And it's true. On the opposite, here you gain several orders of magnitude, so there's no way you could ever approach the same variables like production of heavy particles and so on in fixed target configuration that you will be able to address at CBM. So it is really qualitatively different. It's not that it's only more comfortable to work in fixed target mode in a fixed target experiment instead of a converted experiment at the collider. So I think it's this is indeed, I think, a new realm. Moreover, I must say, from my very, very personal point of view, while some of the CBM colleagues, many of the CBM colleagues, really consider the core of their scientific interest the exploration of the phase transition and the possibility to find a critical point. I think that what really would motivate me to sit in CBM now is the issue of the astrophysics. The possibility of studying the behavior of nuclear matter in neutron star conditions, neutron star merger conditions, is extraordinarily interesting, in my opinion. It's something that, I mean, if I had more time from my directorship, I would definitely pursue myself. I mean, it's fantastic.
Paolo, can I just follow up on this?
Of course. I mean,
yeah.
This was my, on this last part was my private opinion, it's not the opinion of the laboratory.
No, that's very good. That's very good. Is the experiment, can the experiment be geared towards making such measurements? I don't know what are the measurements needed. I have not thought about it, but that's really interesting topic which you have pointed out. If the experiment can be redesigned or designed or can gain we are now still in the design stage or the building stage. If something can be done to push in that direction, can we think about it? I don't know. I'm just asking you.
Paolo, just I want to make a comment on that.
Your microphone is muted.
Sorry, I was muted. The answer is yes and no. Yes, definitely from the point of view of analysis methods. From the point of view of hardware, as you know, CBM has been designed as a very comprehensive experiment, which addresses both hadronic and leptonic variables. You basically measure everything. So I think it is much more an issue of the type of analysis that you develop than of modifying the hardware. So in my opinion, the effort is to really study what, together with the people that do the astrophysics of this, what would be the variables that would really provide essential input for them, and measure those without really needing a new type of hardware. So in that sense, CBM is very comprehensive. So that would not be my first issue. My first issue would really be working on the analysis methods and the variables to be developed. You've seen it in ALICE and in STAR. So much physics has been addressed that was not at all in the original plan. go back and look at what were the variables that people thought would be the most important studies to be done at RIC and at the LHC 2 or 3 years before they started, and what is actually then being done, and it's incomparable. I mean, and I really hope that this will be the case at CBM as well, that there is now, especially the young people that are listening to us right now, there will be new ideas, new approaches that were not thought of at the time of designing the experiments, but that still are within the flexibility of the hardware that is embedded in the way of operating. In particular, CBM works in a triggerless mode, so you actually take all events. So it's really a matter of how you squeeze physics out of them. You don't have the risk that you are actually throwing away the material along the way.
I think if I may add just one statement is that I think what Paolo said is absolutely right. But is we will have all the observations almost, all whatever comes out, and we will have them very fast because of the interaction rate that we will be handling. And I think one of the most important thing which came out from the discussion with LIGO people is that they want to know what is the equation of state of nuclear matter at very high density. And if we know that from the observable, whether it's hadronic or others, because strangeness is one of the most important ones, I think that will shed light to the direction that Paolo might have been thinking to start with. And then, of course, we don't know, as it happens in STAR and ALICE, where we will go will essentially be driven by what is behind.
Okay.
Yeah, so I think Paolo, okay, I think that is right. Thank you for your answer to my question. So I think not only CBM, there are other experiments like Panda, New Star. I think we are aiming for that also. There are a lot of physics lying on that, which has not been explored in other experiment. So along with CBM is there, and CBM is one more interest is that maybe the astrophys we connect, like a gravitational wave, as you mentioned in the beginning, what Subhasis also said. So that will be very interesting to us. Thank you.
Paolo, I have one question which actually this is Vedang here. So which actually a little bit struck me is this nuclear clock. Is it this nuclear isomers which could act as some, say, metastable states in nuclear can act as, is that what you are referring to?
Yes, and the problem is that it is a transition. What people are after are a couple of transitions that are unfortunately or fortunately extremely narrow. And so it has been calculated that if you would go look for them with a laser, for example, trying to catch the right one, it would take essentially forever. So the only way to make a fundamental step there is to measure them from the nuclear side and then tell the laser people where to look. And this is something that can be done beautifully at the storage ring, where you can, actually, these are things that I did not get into. I have a picture, for example, of a nuclear transition in one of our rings, in which you can see the individual nucleus that is circulating, and then that moves to a slightly different state. So the fact that you can measure the individual nucleus is a major breakthrough. And then you give this to the people, once you know the exact transition energy, then you give it to the people that do the next step, that is developing the appropriate laser to excite this transition, and then you make the clock. So it is not for tomorrow morning, the clock, but it is extremely interesting in a world where self-driving cars and so on are becoming a common thing. At the moment, they have to rely on local measurements. They cannot use GPS. The GPS doesn't have the precision. Would you imagine your own car positioned with a nice precision of a few meters? It would be very scary.
Not only that, I mean, if it could lead to, nowadays quantum optics thing are very interesting. This could really lead to nuclear quantum optics, right?
The quantum technology developments, I have not touched at all because I am not an expert, and I would risk saying something.
Because it is similar. Yeah.
But if you want, ask Thomas Stölker to give you a talk about quantum technology developments at FAIR, and you will get to see that there's quite a few very important elements of quantum technology that will be developed thanks to the FAIR facility. I refrain from talking about them because my knowledge is really inadequate, but it's a beautiful field and very promising.
Thank you. Yeah.
Okay, so now, Paolo, so we have one question from YouTube. So we also live telecasted it on YouTube. And since you were a spokesperson of ALICE for 6 years, so this question is related to ALICE more than FAIR. So the question is, what is Higgs boson? Why any particle create magnetic field? So would you like to answer this?
Oh, unfortunately, we are not the ones who have discovered the Higgs boson. The Higgs boson was discovered by Atlas and CMS and not by ALICE. The reason for which one needs the Higgs boson is in the theory in the standard model to give origin to mass of the quarks, and this is a process that is somehow for us is the starting point. We start with the masses which are induced by the existence of the Higgs field, and we see the mass growing because of the strong interaction and becoming and because of confinement and becoming the masses of the hadrons that we observe and that build the nuclei. So, as I said, that was a discovery that was obtained by using elementary particles, collisions at extremely high energy. That is not what we do. We do these are really a bit the two different ways at looking at things. Maybe I should spend a word. I mean, if there's people in the audience which are non-experts, if you're doing it also on YouTube, I mean, I was talking a bit to the people I could see in the Zoom that are colleagues which know these things. But what we do is looking at things. If you look at an object, what you're doing is exactly what we do in our experiments. You have a source of particles, light source, which produces elementary particles, photons in this case. The photons interact with the object that you are looking at, that is your target, then are collected by your eye, which is the experiment, and then processed in your brain, which is the computer center. This is exactly what we do in our experiments. We are using a particle or a nucleus to probe an object, measure what comes out with our detectors and processes to understand how the object is. Then you want to see more details of this. And then you have really two completely different avenues to which you can go. One is to go to higher and higher energies. And this is what is done at CERN and what you needed to discover the Higgs. And you think of when you're looking at the object, you, instead of using light, you can use X-rays and then gamma rays, and up and up and up with the energy, and you look at smaller and smaller and smaller details. And eventually you create your Higgs particles. On the opposite, what you might want to do is say, but no, but I still want to see the global object. What I want is not to go to the small details, it was to the complexity of the system. And so I want more light. So I imagine you had a darkish room and you pump up your light to get more and more illumination of your object so that you can understand in more detail how its overall structure is. And that's what we do. And that's why we need more and more intensity in the beams. In fact, the technical term that in particle and nuclear physics is used for that is luminosity, which is really like in the lamp that you can put brighter and brighter. And then you look at collective features, at structures with your light, which is more and more intense. But this is so. These are really two avenues that go in different directions. That is why two big laboratories like this are complementary to one another. They are not alternative. It's not that one teaches you something that you could then have learned in the other place. They are complementary. Also, the matter that you study. You remember that we were looking much before at the. If I can, no, it doesn't go back. Ah, yes, it does. We're looking much before at the phase diagram of, let's see if I reach it, or if not, of strongly interacting matter. We're almost there, I hope. Yes. Here, okay, this phase diagram, the exploration of different regions of the diagram is completely complementary, because think of water. Moving along this axis is like studying vapor. And there is no way you can deduce from the properties of vapor the understanding of the way ice behaves. It is down here. Here is ice. It's the solid. So the different phases and how the system evolves from one to the other are learned by experimenting in the appropriate region. And it's very hard to infer from one to the other. Sorry, this was very basic for those of you which are colleagues, but maybe it had some interest for those who are not.
Okay, so I think there are no more questions. So we thank the speaker again for this very nice talk and the discussion, the long discussion. And we hope that in near future we meet you, Paolo, sometime in India.
Oh, yeah.
Would be better.
I would very much love that. And so I thank you all for being here, for patiently listening to me. It's not the same as listening in person. I think that are more lively also the presentations in person, but okay, we do what we can. And in particular, I really hope that I will have a chance again to see you all in India soon.
Okay. Okay, thank you. Thank you
Thank
all.
you.
Thank you.
Thank you.
Thank you,
Paolo.
Paolo.
Thank you, everybody. Bye.
Thank you. Thank you very much.
Thank you, everyone. Bye.
Bye.